Okay, guys, just open your Jupyter notebook. Okay. We will discuss today about one-way ANOVA and n-way ANOVA, so and different types of ANOVA also. I will give the explanation of the snippet of code on ANOVA, and before going into the explanation part of the coding, I just give you a little bit understanding, okay, a little bit overview on what ANOVA actually is. Okay, so just wait. Okay, so look, this is one-way ANOVA. One-way ANOVA is used to compare two means from two independent unrelated groups, okay, using the F distribution. Okay, so the null hypo, I will let you know what is what F distribution is, but right now just keep in your mind that it follows F distribution. Okay, so the null hypothesis for the test is that two means are equal. Okay, therefore a significant result means that two means are unequal. Okay, so look, in the Koskalwallis test, which is a non-parametric test, we did it now. We did it yesterday, the Koskalwallis test. Okay, so that is also that also one kind of ANOVA test, but that is non-parametric. Okay, in that case we compare the medians instead of means, because the normality assumptions and another assumptions uh, for parametric test get violated, and so we have to conduct non-parametric test, Koskalwallis test. Okay, so so here when you know that your distribution is following this kind of F distribution, okay, then you can go with this parametric test, that is one-way ANOVA. Okay, so when to use a one-way ANOVA? Okay, so just go through. Situation 1. You have a group of individuals randomly split into smaller groups and completing different tasks. For example, you might be studying effects of tea on weight loss and form 3 groups: green tea, black tea, and no tea. Okay. Situation 2, similar to situation 1, but in this case, the individuals are split into groups based on an attribute they possess. For example, you might be studying leg strength of people according to weight. Okay, you could split participants into weight categories: obese, overweight, and normal, and measure their leg strength on a weight machine. Okay, so what actually the thing is that you are doing this kind of one-way ANOVA where more than 2 groups are present. Okay, because if only 2 groups are present, then independent 2T test is enough. But when more than 2 labels or groups are present for a one party, for one categorical, for one particular categorical variable, then you have to conduct if you to follow the parametric test, then you have to conduct this one-way ANOVA. So okay, so what is the limitations of one-way ANOVA? Will tell you that at least 2 groups were different from each other, but it don't tell you what groups were different. Okay, remember in the Koskalwallis test I told you, just I am opening that one, then you can understand. Just wait. Just wait. Look, I've told you now in the Koskalwallis test, the population medians are same. In the null hypothesis, the population, three population medians are different. Look. Look, in the note part, in Koskalwallis test, there are three more independent comparison groups with five more or more observations in each group in the test statistic. H approximates a chi-square distribution with k minus 1 degrees of freedom. Therefore, in such a case, you can find the critical value of the test in the chi-square table of critical values. Okay, so this is what we know. Because if you have more than five observations in each sample, and also if you want your the categorical variables more than one, then you can conduct those the chi-square. So the now look, in this case, treatment 1, treatment 2, treatment 3 is given, and the sample size for each one is different. Okay. And Koskalwallis test can be used for both continuous and ordinal level variables. Okay. Now look at this. Come to the non-parametric Koskalwallis test. Look, here it is mentioned that, look, the Koskalwallis H test tests the null hypothesis that the population median of all of the groups are equal. It is it is a non-parametric version of ANOVA. Okay, because in ANOVA we compare the means, not median. Okay, the test works on two or more independent samples, because if it is two, then you can also conduct the independent two tests. Okay, if it is parametric, and if it is non-parametric, you can go with man Whitney you test. So it will work on two or more, okay, independent samples which may have different size. Okay. Okay, note that rejecting the null hypothesis does not indicate which of the group differs. Okay, so this is the same case for ANOVA. You can get whether the groups are different or not, but you cannot know which groups are different. Okay. So in order to learn which groups are different, you have to conduct post HOC comparisons between groups are required. Okay, post HOC comparisons between groups are required to determine which groups are different. It is the same case for ANOVA also. Okay. So this is what they are talking. That is the limitations. That if you A one-way ANOVA will tell you that at least two groups were different from each other, but it won't tell you what groups were different. So in order to know that, you have to conduct that post-HOC comparisons. Okay. If your test returns a significant F statistics, you may need to run an add HOC test. Okay. Like the least significant difference test. Okay. To tell you exactly which groups had a different difference in means. Okay. So now come to this two-way ANOVA part. Okay. Okay. Before going to the two-way ANOVA part, I will explain. I will give the explanation of the one-way ANOVA. Okay. Just wait. Look. This is a call center performance evaluation. Okay. Suppose a telecom company has customer care call center at 5 different locations. Okay. So what are those locations? Center A, center B, center C, center D, and center E. Okay. An incoming customer care call randomly gets routed to any one of these 5 centers. Okay. A complaint or call can be categorized as either of the following 4 priority type: urgent, high, medium, and low. Okay. The telecom company wants to analyze how are the different call centers performing with respect to the variable time to resolve. Time to resolve means they take a certain amount of time to resolve the issues. So how first they can resolve these issues. So based on that, they will decide which call center is performing better than the other one. Okay. So here I obviously need to concentrate on the mean of the time to resolve. Okay, mean time to resolve. So I have to, my hypothesis will be like that: the mean time to resolve for all call centers are equal. That is, all call centers are performing equally. And if I consider the alternative hypothesis that at least one of the mean centers is different, then that there is some call centers which is performing better than the other one. Okay, that is the opposite of my null hypothesis. Okay. So in order to test that, I have to conduct ANOVA. Okay. So what is analysis of variance? So just go through. In the call center performance evaluation illustration, we want to examine if the variability of the objective variable, okay, time to resolve a problem or complaint across the grouping variable, also called the factor, okay, call center locations, is significant enough or not. So understood? It means when we want to test the equality of average or mean of the objective variables across different groups of observations. Okay. Recall that in testing of hypothesis, we learned that this is called analysis of variance. Okay, when we compare the mean, then why are we giving its name ANOVA, analysis of variance? Why? We are comparing here means across the groups, across the different groups. Then why are we giving the such name, analysis of variance? It should be analysis of means now. Then, but the name is analysis of variance. Why? Can anyone tell me? Can anyone know? Ujjal, do you know? Ujjal, do you know?
Ma'am, actually it compares the variance of populations mean.
It compares the means. Why do we name it analysis of variance? Because I have told you now, compares the means across the different groups. Okay. Because in the null hypothesis it is mentioned, you have to you are mentioning a statement where it is mentioned that all the population means are equal across the groups. Okay, and in alternative hypothesis, what is mentioned? That is all the at least one of the population means across the group is different. Okay, so here the thing is whether means are equal or means are not equal. Okay, and that is what the null and alternative hypothesis deal with. Okay, but I want to learn that why this ANOVA is named instead of naming analysis of mean. That is it is termed to be as analysis of variance. Why don't we term it analysis of mean? Because here when you go to the computation part, we will learn that then you see you have to find out the ratio between the group variation and also the within group variation, and then you can find the F statistic. Okay, and that F statistic is used to measure the mean across the different groups. So here actually the formula which is used that is the F statistic computed on the basis of the between group variation and within group variation. It is a measurement of the ratio. Okay, we will learn that. Between group means suppose okay, I will show one thing on notepad, or I will show you later. Okay, so now just think, suppose you have three groups: treatment 1, treatment 2, treatment 3. So for the treatment, there will be variations between the subjects of treatment 2 and treatment 1. So that is between group variation. Also treatment 1 and treatment 3, treatment 2 and treatment 3. So this is your between group variation. And within group variation means within treatment 1 there are different values or different data present. So between these elements there is variation, obviously. Okay, because every element does not get close to central tendency. Okay, there is a deviation from the central measure. Okay, central measure of tendency. So central tendency of measure. So obviously there is a little bit deviation from the central tendency of measure of the elements present within the group. So that is your within group variation. So when you compare or when you take a ratio of this between variation and between group variation and within group variation, then you will get the F statistic. Okay, so that will be again used to compare the means across the different groups. We will come to that, how we deduce this. But right now just keep this thing in your mind, and now just we move on with the understanding what an ANOVA is and how it actually works in practice. Okay, so look, analysis of variance is a statistical tool that is used to analyze how significantly means of a variable under study varies from one group to another. Okay. So you have to now understand the business problem. Okay. So what is that? In the call center perform evaluation illustration, the objective variable is time to resolve a problem or complaint. Okay. We expect that the different locations or call centers to have an impact on the objective variable. Okay. Hence, the grouping variable is call center location. This is also called factor. There are 5 different locations. Each location or values of the factor are known as levels. Okay. Or you can say groups also. Okay. So here levels for call center location are center A, center B, center C, center D, and center E. Okay. So collecting and understanding the business data, we select randomly some observations. Here call at each of the sales centers. Okay. For each of the observations, we observe the value of the objective variable. Here time to resolve. Okay. If the number of observations from each level of the factor is same, for example, in the above table, it is 10. Okay, for center A, center B, center C, center D, center E, all the observations are same. That is 10 observations. Okay, then the model is called balanced model. Else it is known as unbalanced model. Okay. What we have found out in Koskalwallis, unbalanced. Okay, different samples of different size, and that is a non-parametric one, which we have conducted. But here, what we are telling, that is, if for unbalanced ANOVA we have to do some sort of little bit modification. That is not our concern here. Main thing is this: when the sample size are equal, then it is called balance, and when it is not equal, then it is called unbalanced model. Okay. We work with an example where the sample size is equal. Okay. So we work with a balanced model. Okay. For conducting the one-way ANOVA. Now formulating the business problem. How to formulate? Okay. Just go through. I'm giving you 3 minutes to try to understand. Suppose Yij is the time to resolve the ith problem at the jth call center. Okay. So we want to check Y by j, the average time to resolve for the jth call center is different for different j. Okay. Understood? Now each Yij will have 3 components. What are those? The overall average time to resolve, let's call it mu. Okay. Effect of jth call center, positive or negative, let's call it alpha j. A random variation, let's call it epsilon ij. Okay.
Ma'am, here in second line, jth call center is different for different j. What is it means?
Yes, for different j, because when I am talking, we want to check yj, the average time to resolve for the jth call center. Okay, at that time the jth call center maybe call center A, call center B, call center C, call center D. So you have to compute all the time the yj for different j. Okay, whenever you are choosing one j, that becomes the jth call center, and have to compute the corresponding y bar j. Okay, that is the average time to resolve. When we come to that mathematical part, you can better understand. Look, so the model becomes yij equal to mu plus alpha j plus epsilon ij, where yij is the value of the objective variable, here time to resolve for the ith observation from jth level. Okay, mu is the overall effect, alpha j is the effect due to jth level of the factor, here jth call center, with summation of alpha j equal to 0, and alpha j is not equal to 0 for at least 1. Okay, that is the summation of alpha j is equal to 0, but when you are considering a single alpha j, that is not equal to 0 for at least 1, for at least 1 j, that is for at least one call center, this alpha j is not equal to 0. Okay, and epsilon ij is, is the random effect. This model is called one factor ANOVA model. Okay, so when you are framing the hypothesis to test, mean of y is same across all levels of the factor. Under the assumption of null hypothesis, the model reduces to this: yij equal to mu plus epsilon ij. Okay, so we rewrite the null hypothesis as alpha j equal to 0 for all j, and the alternative hypothesis will tell you alpha j is not equal to 0 for at least one j. Okay, so one factor ANOVA model assumptions. If these assumptions get violated, then we conduct non-parametric test Koskalwallis. Okay, the observations are independent to one another, that is time to resolve for one problem is independent of that for another problem. Okay, observations from each group, that is levels of factor, are selected randomly. Okay, the objective variable, here time to resolve follows normal distribution at least approximately. Okay, variation of the variable across levels, that is homogeneity. Okay, variation of the variable across levels is constant. In other words, for j level, the objective variable yij follows a normal distribution. Okay, the normal distribution belong to the will be like that: n within parenthesis mu plus alpha j comma sigma square. Like the sigma square is homogeneity of variation, na? That will be same. Okay, that will be constant. Okay, across the different levels, the variation of the objective variable is constant. Okay, now test for homogeneity of variance. We have to check the last assumption, okay, before we proceed to ANOVA. So we will do ANOVA only if the last assumption is valid. Suppose for k levels of factors, the standard deviation of the jth level is sigma j. Now we test whether sigma 1 square equal to sigma 2 square equal to dot 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 sigma square k square. Okay. Understood? So J means key. Then jth label for all J. So what are the values of all J? That is 1, 2, through 3, 4 through K. So we will test here sigma, whether sigma 1 square equal to sigma 2 square equal to sigma 3 square equal to dot 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 equal to sigma K square. Okay. So this test is known as test of Bartlett test of homogeneity. Okay. Okay. Now, if the p-value of the test is low, we reject null hypothesis and then standard ANOVA is not valid with the data. If the p-value of the test is greater than 0.05 or 0.01, we fail to reject the null hypothesis and proceed with ANOVA. Understood? Now, this is your one factor ANOVA table. The tool to do ANOVA is known as ANOVA table. It looks as shown below. Understood? This is your factor, okay, k minus 1, because you know there are k labels or k groups are present. So degree of freedom will be k minus 1. So this is your sum of squares, okay. And for error, the degrees of freedom will be n minus k, okay. N is your total number of observations, so n minus total number of variables, so n minus k, okay. So that will be your sum of squares of errors, okay. And when you take this ms mean squares, okay, so you have to divide them by degree of freedom, okay. Then you have to compute the f statistics, that is the ratio of mean square, okay. That is how you are computing this f statistic. I will elaborate these things. I will tell you how to work with between variation and within variation, okay. Then you can understand, okay, what what actually this SSE means, okay. Sum of squares for error, okay, or sum of squares or between groups, okay. I will tell you. This is a generalized form, okay. You have understood the statistics is computed based on the mean squares of this SSA and SSE, okay. So this is and then based on that value we decide whether the means across the different groups are equal or not, okay. So total sum of squares, total variation in the data, okay. J equal to 1 through k, that is what for different j, okay. I equal to 1 to nj, yij minus y bar 0 0 whole square. Y bar 0 0 is the grand mean of all data. Whatever be the observations you are having, you have to take a mean on that, okay. And for each data point will be subtracted from that, okay. It is your grand mean, that is yij minus y bar 0 0, that is grand mean will be subtracted from each data point and take a whole square of that. And for each cell, for each level, you have to do that, okay. So k is the number of labels and nj is the number of observation from jth label, okay. Suppose j equal to 1, then you have to compute these for first label, and there will be n number of observation in the first label. So I equal to 1 to nj, okay. That is the main thing. Then if your j is equal to 2, then you again for the second label you have to subtract the grand mean, the total mean of all data from the corresponding elements present in the second group, okay. This is how we move on. This is called total sum of squares. Okay, that is the total variation in the data. Now effect sum of squares, that is the between effects variation in the data. Okay. Between effects variation in the data. Okay, that is between variation in the groups. Okay. So what is that? Look, j equal to 1 through j equal to k nj y 0 z y 0 0 whole square, where y 0 z is the mean of the observation from the jth level. Okay, in the data, and k is the number of labels. That is your grand mean is subtracted from the group mean. Okay, understood? Group mean. So that is your group mean. Okay, that is for the first for the call center A, there is a mean. For the call center B, there is a mean. For the call center C, there is a mean. And you know, for all the data, that is for call center A to call center 5, you have a grand mean. So you have to deduct the grand mean from the respective group mean and square it. Okay, that is your between effects variation or between groups variation. Okay, so that is also termed as sum of squares. Sum of squares for association, you can say. Now here are sum of squares. What is that? The extent of total variation in the data, that is sum of square of total that is not captured by effect sum of squares, that is SST minus SSA. So how can you find out this? Look, Yij minus Y bar 0z, that is your group mean minus individual observation of that particular group. Okay, suppose call center A has a group mean. Okay, look at the figure. Suppose this call center A has a mean, so then that mean will be deducted or subtracted from the those elements present in the call center, from the values present in the call center A. That is, suppose the group mean is 500, then 500 minus 217 plus 500 minus 84 plus 500 minus 169. You have to move on up to 500 minus 71 and take a sum of squares of that. That is your sum of squares of errors. You have to measure sum of square of errors for each level in this way. Okay. That's why I equal to 1 through nj and j equal to 1 through k. Okay, Yij minus Y bar 0z. Understood? Now, understanding the degrees of freedom. Now look at the formula first. If your mean square, that is between group variation by and mean square of error, that is within group variation, is taken as a numerator and denominator part for computing F statistic. Look, MSA by MSE. So if your MSE is small, then MSA gets larger. Okay. If your MSE is small, then MSA gets larger. Okay. So that is your between variation is much more. So there may be chances that the mean across the groups are different. And if your MSE is larger, then MSA becomes small. Then the between group variation is smaller compared to the within group variation. Okay. And in that case, you can say no, that the deviation comes due to chance, because epsilon term is your error term, whatever you have introduced in your model. So that is not whatever variation takes place, that is not due to alpha j, on the effect of the that is the effect of that is not due to this that is not due to this alpha j effect on the jth level. Okay, so then you can conclude that uh, alpha j equal to 0 for all j, and that is your null hypothesis. You can retain with the null hypothesis at that time. Okay, because when MAC is large or MSA is small, okay, when the value of MAC is uh, greater than the value of the MSA, then obviously your F statistic computed here will be small. Okay, so so that will also lead to the conclusion that your means across the groups are equal. Okay, that is whatever variation you have found out, that is due to the within variation, that is due to chance or due to the epsilon term you introduced in your model. Okay, but that is not due to the variation between groups. Okay, so you can say population means are equal if the p value is measured against the alpha level 0.05 or 0.01. Okay, you can get that. Okay, it depends on the different values on our data, but I am just telling you what happens if MSA is greater. If MAC is small, then MSA based on that, if statistic is whatever you have computed, that in that case, if MSA is 5, okay, and MAC is 1, okay, that means MAC is smaller compared to the MSA, that is within group variation is smaller compared to the between group variation. In that case, f is equal to 5 by 1 equal to 5, and if you increase MSC, okay, look, it will be 2, then 5 by 2 is what, 2.5. So if you increase the within group variation, obviously the F statistic gets decreased. Okay, so if your MSA, that is between group variation, is 1 and MSE is 5, then what happens? 1 by 5. Okay, so that will be your point 2. Okay, so this is the, so in that case your f becomes small. So why does it happen? Because your MSc is at that time is smaller than MS, because your MSA is smaller than MSc. You have found out, suppose MSA 1 and MSc 5, then obviously your f is 0.2. So MSc is much, so MSc is more, the value of MSc is more compared to MSA, that is within group variation is more compared to between group variation. So in that case, obviously you tend to the decide, it just leads you to the conclusion that your population means across different groups or levels are same, because the alpha j is for, that is the effect of, that is the effect of alpha j on each j factor is equal to 0. Okay, so that's why you can conclude that. Okay, so obviously you have to consider the data given on your given in a particular data set. Okay, but if this is the value which you have got, suppose you have got MSA 5, MSc 1, say by some sort of computation you have got such, then what will happen? Or if you get the reverse, that is MSA 5 and MSc 1, and MSA 1, MSC 5. Then what will happen? So you have to learn that. That is you have to play with the numerator and denominator values of MSA and MSC. Okay, and based on that, you have to compute F statistic and try to understand what happens. Okay, and from that you can understand that is when your between group variation is more compared to MSC, then obviously there is a chance that your alpha, at least one alpha j is not equal to 0. And when your MSA is less compared to MSC, okay, so there is a chance that the alpha j is or the j factor is equal to 0. That is the whatever variation it takes place, that is due to within group variation or error epsilon introduced during the model, not because of alpha j. Okay. So now try to understand the degrees of freedom. Degrees of freedom is the number of values in the final calculation of a statistic that are free to vary. Okay. It can be looked upon as the independent coordinates in the estimation of some statistical measures. Okay. Degrees of freedom of sum of squares, effect of sum of squares is k minus 1 as summation of alpha j equal to 0. Okay. Degrees of freedom of sum of square, total sum of square is n minus 1. Because summation of this yij minus y bar 0 0 equal to 0. It is not whole square. Okay, look at this. It is not whole square. The whole square value is something else. Okay, look at this. Look, this is, there is a whole square. The whole square value will be something else. Okay, but when you are considering only the summation part without the whole square part, then that is equal to 0. You know that whatever be the, when you deduct something from the mean position, when you deduct the values corresponding to the mean positions, then the addition of the deviations, whether the negative terms whether the negative terms are present or and positive terms are present, they, after adding all these things from after adding all the deviations, that is, you have to subtract the data, the values from the mean first, and then you have to add these. Then this summation for each observation and for each level will become to 0. If you consider only for each observation first time, then it becomes 0. And when you are doing the same thing for kth level or for kth groups of a particular factor, then it will obviously become 0. So that is the main thing. And and degrees of freedom for SSC is obviously n minus k, which is degree of freedom for SST minus degree of freedom for effect of squares. Okay, effect of sum of squares. Okay, so this is the case. Understanding the mean squares and the F statistic. We'll calculate the mean square of factor and error, okay, by dividing the corresponding sum of squares by their degrees of freedom, okay, and It is the ratio, the F statistic is the ratio of MSA to MSE. This is the test statistic for ANOVA. The corresponding p-value of the observed F statistic is the p-value. Okay. So one factor ANOVA table is that. Okay. So now we have to look at the illustration part. Okay. So this is the data. Okay, I'm sharing the notebook. You all just open the notebook. Okay. Have you all run this file? Have you all run this file? Have you all got this output after running this snippet of code? Guys, have you all run this?
No, ma'am. We have to.
What the same output? Got the same output? Ujjal, Shima,
I'm just
Check.
executing.
I cannot get your response. Be a little bit louder.
Yes, ma'am. Getting the same output.
Okay. This is the output, okay? Okay. So look, what I have done, that is have just used the box plot, okay, by center. Okay. Now I have to call the group by function to get the group mean, okay, and also the group by variation. Now I have conducted the Bartlett test, okay. Now look, this is how we do, okay. Bartlett calls A time, calls B, calls C time, calls D time, calls E time, okay. Then look at this. You can print this value, okay. If you want to print, you can get the value, okay. I have not printed out, but you can print this value, okay. Okay, just do one thing. Wait, it is executing. So look at the Bartlett's result. It follows normal distribution. 0.23 is greater than 0.05. So we can say that the objective variable is follows normal distribution. The objective variable is across the different groups is following homogeneity of variance. Okay. So you can also conduct Shapiro test for normality, but here the main concern is checking homogeneity. So p-value suggests that for a given alpha level 0.05 or 0.01, the p-value is greater than that one, and so we can return with the null hypothesis that the homogeneity of variance across the different groups is same, and we can move on to conduct ANOVA, one-way ANOVA. Okay, because there is only one categorical variable present and more than two groups are present. So now look at this ANOVA part from stats model. We have to import this ANOVA underscore LM, that is linear model. Okay, OLS stands for ordinary least square. Okay. I will talk about OLS later in linear regression. Okay, but right now just try to understand that it will just give the it will just build the model which I have shown, that is SSA, SSE, okay, MS, MSE, okay. So this is, and it will just give you the results when you just call the fit, okay, on this model, okay. And then look at this. Okay, just wait for 1 minute. now look at this part. That is, I've just used fit method on this model to improve accuracy, so that the parameters used here can adjust itself and give me approximate output with which the model was actually trained. Okay, that is, it just generalize the data or input given with which uh, the model was actually with that type of similar data the model was actually trained. Okay, so so fitting means just approximating to the output or giving accurate results. Okay, by adjusting parameters in the model. Okay, so now this ANOVA linear model just accepts that results. Okay, and here you can learn about the type 1 error, type 2, type 3. These are not that alpha error or beta error. Okay, that is something related to when you compute, that is related to the computation of the mean squares. Okay, if statistics. Okay, so in that case you have to take some of errors like type 1, that means sequential order error. Okay, sequential order of sum of squares, that is, I will tell you what does it mean. Right now you just keep in your mind that there are three types for calculating these squares. Okay, for the sum of squares between and within group variation, that is type 1, type 2, type 3. Okay, and then this you have to print this ANOVA table. Just wait 1 minute. Now look at this. In order to learn which call center we have to reject, for that we have to do two sample t-test. Okay, that is post HOC test, you can better say. I have conducted here sample t-test. You can do any add HOC test. We will I will tell you. You will learn that one when I conduct two-way or n-way ANOVA, but you can also conduct a two sample t-test as well. Okay, so for scipy dot stats, you have to import this and then call on this. You have to do it for the rest 9 groups. That is, if it is calls A, calls B, then calls A, calls C, calls C, calls A, call D, calls A, call E, then again calls B, calls C, B, D, B, E, then C, D, C, E, and finally D, E. So you have to do it for the rest 9 groups. Okay, so you have to consider here equals variance equal to false. That is the variance between these two groups, call A and call B, is not equal. Okay, while conducting this sample 2 test. Okay, 2 sample t test or independent t test, you have to consider this. Okay, so now look at the output part. Okay, so so before you have to print the ANOVA table. Okay, look at the ANOVA table center. This is sum of squares, this mean square, this residual is this, a statistic is this. Okay, and then this is your PR value. Look, 0.019. Okay, ready, and if you consider 0.05 your alpha level, so 0.019 is greater than 0.05, so you can retain with the null. That is, the population means across the different groups are equal. And if it is 0.01, that is, if your alpha level is 0.01, then your p value is less than 0.01. Okay, that is 0.019 is less than 0.01. So in that case, you have to go with the alternative hypothesis, and that means there is a significant difference in mean present in at least one of the groups. Okay, so in order to check that, we compute this. Okay, look here, there is no difference, no variation presence between these statistic, this. Okay, so if I do it for the rest 9 groups, I do that for you, that will be good. Okay, so if I run again, look at the value, look at the p value, and come, look this value here and here. So what is this third last and fifth last? Third last is this CD, and fifth last is BD. So look, there is a difference between CD and BD. Okay, look, because the p value is less than 0.01. Okay, 0.013 is less than 0.0, oh sorry, 0.013 is greater than 0.010. Okay, for only this one. Okay, 0.0100010. Okay, in that case, so their third list is what value? This is C and D. So in that case, you can say the variation present in this group. Okay, because of which the population means are not equal. If you consider your alpha level to be 0.01. Okay, so but which groups are different, that cannot be learned from ANOVA table. You have to conduct this independent 2T test. Okay, so this is the group. Okay, because 0.0, the p value for that group, when you are conducting t test, independent t test, you have found out the p value 0.0010, which is too small compared to the alpha 0.01. Okay, so if you look at this box plot, okay, then you can learn that. Look, if you look this C and D, look, the difference, there is a obvious, there are obviously an outlier present between C and D. Okay, and now look, there is another one, this D and D, 0.09. Okay, 7. So 0.097 is also so you can say 0.097 is also less than what? 0.01. Understood? 0.0976 is also less than 0.01. So, so this one and this one. Okay, so look at this. So here D and D and here C and D. Look, in that case, on main difference is C and D. Okay, so that's look, how does this difference happen? How does this difference take place? The median is the position of the median is much more the position of the median is more higher. Okay, so the position of the median is higher than that of the position of median of center C is higher than that of center D. And also an outlier is present in center D, okay, which is not handled in the data, so that causes variation. Okay, and look at the maximum position of this center C and center D, and the minimum position of this center C and center D. If you look at the center A and center B, the median is not that much the position of the medians are that not much different. Okay, and the spread of the mid portion almost same, or the whatever the distribution it is having, there is a similarity. But when you, and also you, if you come to this if you come to the if you come to the part while comparing center B and center C, you find the medians and the distribution among the middle across the middle part, and also to the extreme left and right part is covering the same area. Okay, but and if you but the difference when you are considering A and D, okay, then also look, the median of A and median of D is not that much different. Okay, also B and D does not have that much different, and also, but if you look at the D and D, the median is not that much different, but there is an outlier present, and the outlier is somewhat different. And look at the mean value part of center E and the minimum value of center D. Okay, so there is a difference. So in that way, you can get an idea that which is making the main difference. Okay, which is making the main difference, which center is creating the noise here. Okay, the difference here. So based on that, you can decide. Okay, suppose I'm taking just wait. Suppose look at this. This part call it the compare where we compare the mean time of different groups, call A, call B, call C, call D. Look at this call C. Okay, and creates the main nuisance here. Okay, so if you remove this call C, okay, uh, because look, this 0.043 call, when you compare call C with call E, okay, 0.043 is less than 0.05. Okay, if you consider alpha level to be your 0.05, it is also less than. So main problem is with with the group C. So if you remove this group C level, okay, just you can copy your Excel sheet, give you the name of the Excel sheet, customer care mod, okay, and remove the column C and rerun the code, okay, then you will get that the value that is the mean across the different groups, or across the groups become equal. That is, there is no significant evidence which can support to fail the to fail or reject the which can support that we can reject the null hypothesis. We have to retain with the null, but only after removing the column C. Okay, that is not column, only after removing the level C or group C and the corresponding data from the time column. Okay, so that is what you have to you can do. You can modify your Excel sheet. You just simply copy the Excel sheet provided to you, that is customer care.csv, and give a new name, customer care mod .csv, and remove the C level, and that is called C data, and the corresponding values present in the time column. Only retain the call say, call A, call D, call say, call B, call D, call E, and the corresponding data present in the time column, and rerun the code, okay, using the customer care mod .csv. Then you can find out that all whatever the differences you have found out in the independent 2T test while comparing the two groups, that that shows only that shows only what I can say, that shows that there will be no variation between two groups. So it ultimately leads you to the conclusion that your ANOVA that your one-way ANOVA model what you have built is following null, okay, hypothesis. That is the population means across the different groups become equal. That is, you will get in the print ANOVA table, the p-value will be something else that is greater than 0.05. Okay, so then you can go with the null hypothesis. In that way you have to work, okay, in that way you have to think. And you can check also this t-test in results, okay, that is independent t-test results, whether any variation exists between the groups or not. Okay, so this is the this is how you can convert any ANOVA model where you have found out that you have to reject null, then you have to find out the group which creates this deviation or noise in your model, and then you can rerun your code. But it may happen that you cannot build your model every time by removing a particular level. So in order to handle that situation, you have to learn how to handle outliers, how to standardize your data, okay, make it unit free, and make the data standardized, and use some use the standardized values for computing ANOVA tables. So that is what we have to learn. But right now, just learn if these things happen, then how can you how can you deduce, how can you conclude? It is better to use how can you conclude or interpret your results. Okay, it is obvious you can remove center C and make your model sufficient enough, but that is not what you can do, because removing some data is not good in practice. So here you have to go with the alternative hypothesis, that is you fail to reject the null. Okay, yes, there is at least one group which is performing better than the other centers, okay, than the performance of the other centers. So you have to accept it. Okay, so you have to go with the alternative ones, that is you fail to reject null because you have not and what will be your explanation? Because the p value is less than 0.05 level, okay, which you have got from the ANOVA table, and while computing the F statistic for this data set. And you can also say that you whatever sample size you have got is not enough to conclude that the null hypothesis is true, that to retain with that you can retain with the null hypothesis. Okay, so you don't have that much sample size at your hand, at your hand right now. So that is another way of interpreting. Okay, so that's it. So this is what one way ANOVA. Now we come to the n-way ANOVA part. Okay, so before that I am giving you 10-minute rest. Okay, and then I come to that. Okay, just go through whatever I have covered up to this point in the last session, and also today what I have covered. Okay, just go through. If you have any question, ask me. I'm giving you 10 minutes. Okay.
Hello, sir. Sir, ma'am will continue the class or not?
That's why I ask you able to audible. I'm able to you.
Voice is breaking, ma'am.
Ma'am, your voice is not coming properly.
I cannot see from your side. Now my voice taking order interconnect. Oh my. This is another. When my Jar, are you there?
Hello.